Hi everyone. Bear with me as I try to get through some components of the lab through video. So this is our Fabius GS Premium Anesthesia machine made by Draeger. There is our patient monitor. This is, I'll stand back a little bit. This is basically the whole anesthesia machine. This is our anesthesia drug cart, some syringe pumps to give some medications. So just back to the anesthetic machine here. Just going to go through labeling some of the components. So you have a diagram in your lab. This might not be the right order that I'm going in through, but I will go through all the parts. So basically, this is your inspiratory valve. This is your inspiratory port. This is your patient circuit. This is your expiratory port. This is your exhalation valve. We have an O2 sensor that will sit in the inspired side, and that is just taken out in between cases or at the end of the day to try to prolong the lifespan of the cell. The top of the machine here, this is your PEEP and your PMAX valve, which closes your exhalation valve to deliver a PEEP. This is your APL valve. This is your APL bypass valve. So during ventilatory modes, this APL valve is taken out of the system. Basically what the APL valve is the adjustable pressure limiting valve, and this will help direct flow into the breathing bag for manual and spontaneous breathing. So during spontaneous, we don't want any resistance. We want the patient to get 100% oxygen, so we don't want rebreathing to occur. And once the patient goes off to sleep, we can close this valve. It kind of depends on how much of a leak that you have when you're bag masking, and this pressure gauge will correspond to the pressures that the patient is getting when you're bagging. So we want to keep the pressures under 20 centimeters or under 10 centimeters of water, because that's kind of, or I guess between 10 and 15, that's kind of when the esophagus would start to open. So we want to limit the amount of air going into just the lung and not the esophagus. Once the patient's on the ventilator, this APL valve kind of is not in the circuit anymore. This is our breathing bag for the circuit. Our circuit has the elbow, the filter HME, a port which has a CO2 sampling line, and that goes all the way up to this machine. And that's what's going to draw our exhaled gases and measure them. So on our patient monitor, you can see me in the reflection there. Once it comes up, we have our EKG reading at the top, our touch screen, our SAT, and then our CO2 tracing. So that's where we're going to see our square waveform. Our blood pressure will be down here. When we're pre-oxygenating, you're going to keep an eye on your end tidal oxygen. That is what shows you that our patient is being adequately pre-oxygenated. We want to have denitrogenation. So basically filling the lungs up with as much oxygen as we can. I'm just going to turn this monitor back into standby. The face of the machine here, we have an auxiliary flow meter. So this is what we hook up our patient's nasal prongs to. This machine is driven by a piston, so that's the piston inside. If you look on the lecture notes, there's a couple of different methods of delivery. There's a piston and there's also bellows. So the notes explains the difference between those. Anesthesia ventilators are quite straightforward. So we have 4 different modes: volume control, pressure support, SMV with pressure support, and then manual spontaneous. We have a total fresh gas flow meter. So because we have digital displays, we can deliver nitrous, air, and oxygen. Because we have digital displays, it's more accurate than the flow meter. So we just need like a total flow meter in case our backup battery died and we didn't have digital displays anymore. If the machine has a power outage, you can still deliver a manual anesthetic, but the backup battery does not have enough power to provide ventilation. So you would just have to close your APL valve a little bit and squeeze the bag. All right, let's go through the 4 safety tests that we perform in the morning when checking the anesthesia ventilator. So this machine is made by Draeger. If you've learned the baby log, it is quite similar, some of the components of the machine. The first test is the run system test, and this basically checks the electronic components and the software, making sure that the machine is deemed functional and safe for use. There's 10 different tests that it goes through. If everything passes, it'll say functional. If one does not pass, it'll categorize it into conditionally functional or non-functional. If it's conditionally functional, you have to acknowledge it by pushing the knob to get it into the home screen. If it is non-functional, then you cannot use the ventilatory modes on the ventilator. Something that could be conditionally functional was, say, the backup battery didn't charge enough, and that is just warning you that it didn't charge, and you have to acknowledge that before you can actually use the ventilator. This machine has 2 sensors that need to be calibrated every 18 hours, so once per shift usually. The first is the flow sensor, so we just push the button. It gives you instructions on how to go about with the test. We want to make sure that our flows are all off. We remove the expiratory hose from the machine, and then we push the knob to start the flow sensor calibration. Basically what happens, you can see the piston moving up. It's drawing in room air through this port. There is a flow sensor that sits in here. It has 2 heated thermistor wires. When the flow goes by, it causes a temperature drop in the wires, and then that is calculated on a constant. And when your patient is on the ventilator, it will then be able to measure flow coming from the patient. Depending on your frequency set, then that is how your exhaled volumes will be calculated. So it'll prompt you that it has been completed and to reconnect the expiratory hose, which I have already done. The second sensor to calibrate is the O2 sensor. That is what I showed you at the beginning of the video. So basically it prompts you again, remove the O2 sensor. So just basically removing it from its housing there. We want it exposed to room air for 2 minutes and press the knob to start the calibration. So both that test and the flow sensor test are quite quick. They don't really take a lot of time. All right, so that has been completed. If we were to use the machine, we would reinsert it into the inspiratory port at this time. I'm gonna leave it out because we're not actually using it on a patient. The last test that we do is a total leak and compliance test. It's gonna make sure that there's no leaks in the ventilator and also measure the compliance of the disposable circuit. Again, the instructions to help you get through this test. We wanna make sure that all of our gases are off. If we had a gas flowing, it could compensate if there was a leak, and then we wouldn't know if there actually was a leak or not. We've sealed the Y piece onto the bag mount. The sample line connector, you can take the sample line out and seal that off as well. As long as our anesthesia gas monitor is in standby, which it is, it will not interfere and cause a leak in the system. What we do is we then close the APL valve between 40 and 50, and then we push the O2 flush button, watching the screen or the pressure gauge to build up a pressure between 15 and 30 centimeters of water. If I was to go over, the high pressure safety relief valve would just vent open, and then I would have to do it again. So this test is now in progress. It takes a couple of minutes to complete. You can see the last 5 tests that have been done. If there is a leak, it will basically calculate it into ventilator leak or system leak, and then it also measures the compliance of the circuit. So you can see the last 5 compliances are very similar. If we were doing more with pediatrics, where the compliance, if it was different between circuit, that could technically affect our tidal volume delivered to the patient. But in adults, we only do this test once in the morning, not every time a new circuit is put on. We do a manual leak test, which just involves closing the APL valve and pushing the O2 flush button, watching the pressure gauge to build up a pressure to ensure that there are no leaks in the system. And I'll show you that as soon as this total leak test is finished. So everything has passed. If there was a leak, I would tighten my connections, making sure that there was no gaps in the breathing system. There are other things that we can check, and if it does break up into ventilator leak versus system leak, again in the supplemental notes, the components that could be responsible for the leak are listed in there. At the end of the test, we just reopen the APL valve and the machine is ready to go. I'm just going to simulate a simple leak test of what we do when we put on a new circuit. So we just close the APL valve again, push the O2 flush button to reach a pressure between 15 and 30. And then we just give the bag a couple squeezes just to generate a bit higher pressure to make sure that there's no leaks at higher pressures. As long as the needle doesn't drop, then you're good to go. So we release the pressure on the APL valve, and the machine is considered checked and ready to go. So we do that every morning. You'll be learning that as a student when you come here throughout your rotation. There are a couple weekly tests that we perform to make sure that safety components of the machine are met. We are not able to deliver hypoxic mixture to our patients, so we know that if we turn up the nitrous, nothing happens. As soon as we turn up the oxygen, only then will nitrous jump up, and in this machine, it keeps the nitrous to oxygen ratio at 25% oxygen to 75% nitrous. So that's the minimum. The Sork assembly is the oxygen ratio controller device, so that minimum oxygen to nitrous ratio. And when we're pre-oxygenating our patient, we just turn the oxygen up to usually about 8 liters per minute. If the patient is taking really big breaths, they may start to draw in some room air, so then we would have to further increase this, and it only goes to about 12 liters per minute, and it stops there. All right, to answer a few questions on the lab, it talks about alarms. The machine is now in standby. I'm going to go to the home screen. We can turn on alarms on this machine. There's only 3 types of alarms. So oxygen, your high and your low, minute ventilation, your high and your low, and then pressure, so your peak pressure and your low pressure alarm. So those are the only alarms. It's pretty straightforward. Let's see what else we can answer on your lab report here. So I've showed you a lot of the components, if there's anything that we're missing here. These are the vaporizers right here. This is our sevoflurane, this is our desflurane. We'll come back to those in a few minutes just to explain some safety features about those as well. I've showed you the ventilator, the airway pressure gauge, the fresh gas hose. This is this black hose here, so it'll be the black hose on the diagram, and then the clear hose is the ventilator hose. So it's coming from the piston to this block here that's called the cozy, and then it goes to the patient's circuit. The gray hose is then now our scavenging, and that goes to the side of the machine, which converts to the pink hose, and then that goes all the way up to the stack and gets vented outside. In your notes, you'll find the difference of 2 types of scavenging systems, the active and the passive, so you can get the information from there to describe the difference between those guys. I'll bring around to the back of the machine here. We have backup tanks, so we have e-cylinders of nitrous, medical air, and oxygen. So in the event of a pipeline failure, this is our pipeline connections, and you can see where they connect to the back of the machine there. In the event of a pipeline failure, then we could turn on the tanks and have gas delivered that way. There is a on-off switch on the back of the machine here. We always keep the ventilator on and ready to go unless we're transporting it from one room to another. Then we would turn it off and then turn it back on when we were ready to use the machine again, or say it's in storage not being used, and we would leave that off. Ventilator control panel, so that is there. Absorber, that is the canister down here. So also in the notes you'll learn about CO2 absorbent. Basically anesthesia circuits, the gases are rebreathed to help conserve the inhaled agents like the sevoflurane and the desflurane. The only gas that we do not want to rebreathe is carbon dioxide. So we have to take that out of the circuit, and that is done by the CO2 absorbent. The CO2 absorbent that we currently use today is called litholine, and you can read about that in the notes as well. Safety requirements of the anesthetic machine. I have uploaded the additional reading for safety requirements, and you can get the information for the lab from that. Where is oxygen related in location to the other gases? And where is oxygen located in relation to the patient? Well, oxygen has to be downstream or closest to the patient. So our goal is to not deliver a hypoxic mixture to the patient. So if we had oxygen, nitrous, and then the patient, we know that we can't set a hypoxic mixture because it won't allow me to turn up nitrous without oxygen. But say there was a leak that developed between the oxygen and the nitrous source, so our oxygen would be leaking out. The patient could then potentially get a hypoxic mixture. We would be able to keep an eye on that with our oxygen cell, but we need to keep a close eye on that. What else here? So oxygen is closest to the patient and downstream. How are the vaporizers aligned? Well, again, we need to have the most potent closest to the patient. So same kind of idea. We don't want a leak developing between the vaporizers so that a more potent gas could potentially contaminate a less potent vaporizer. The vaporizer interlock device prevents us from turning more than one vaporizer on at a time. So there's pins. It pushes forward so that I physically cannot turn on the other vaporizer. That's a safety feature of the vaporizer. So how are the vaporizers aligned? The most potent must be closest to the patient. So basically, if you think about your MAC values of the different gases, you'll be able to sort out which one is more potent of the three and closest, and then the second most potent, and then the third most potent. So you guys can answer that. Also in the notes, desflurane does have a different vaporizer. Basically, we heat it to maintain a constant temperature. It's heated to 39 degrees Celsius and pressurized to 2 atmospheres. The two factors that make carbon dioxide absorbent change color is the CO2 exhaustion and being dried out. We've gone through the ventilator alarms. Also in the notes, you can, actually in the supplemental Fabius gas machine notes, it'll show you the path of delivery or the path of gas, so right there. So that will answer question number 9. That'll help you there. Scavenging, again, you can get that from the notes. And we've gone through the machine. You should be able to label all of that. And the pneumatics, give that one a try. If you have any questions, you can let me know. At some point I will post the answers to the lab so that you guys have all the information. And again, I've already gone through the COSY or the compact breathing system top view there. So just wanted to give you a little idea. Sorry again, we can't go through the lab, but at least you're able to kind of see what the anesthesia gas machine looks like. So again, email me if you have any questions. Take care, guys. Bye.